Hello everyone, my name is Jose Tiznado and today I will be speaking about edge detection in self-driving cars. In this video, I'll be going over what role does edge detection play in self-driving cars, and I will demonstrate how to implement a program that processes a picture of the road and detects lane lines. As mentioned in my previous presentation, edge detection algorithms are used in self-driving cars to set the steering wheel angle based on the lane lines detected on a picture of the road. Now let's get into the tutorial. So before we go into the first step, we will set up code to be able to display our image. And the first thing that we're going to want to do is to import the library CV2. And we will do this by typing import CV2. Then we will be making use of the imread function, which reads our image and returns it as a multi-dimensional NumPy array containing the relative intensities of each pixel in the image. So we will create a variable called image, and we will set it equal to cv2.imread. And for the argument, we will write the file name as a string, in our case, road.jpg. Then to display our image, we use the function imshow, which takes two arguments, a name for a window that is going to display our image, and the image that we want to display. So we type cv2.imshow, and we're just going to call our window test, and then the image that we want to display is our image. And finally, we follow it up with the wait key function to display our window infinitely until we press anything on our keyboard to exit. And we do this by typing cv2.waitKey and choosing a parameter of 0. And as you can see right here, this argument is a delay in milliseconds, but the number 0 is a special value that means forever, which means it'll keep displaying our image infinitely until we press any key on our keyboard. Now to test this program, we save and we run. Oh, my bad. We run by typing Python, then the name of our program, which is lanes.py. We run that, and as you can see, it opens up a window called test, as we set it right here, and we can display our image. And now, as you may remember, the first step for our edge detection program is to create a grayscale version of our original image. And for this step, we're going to need to import another library, which is called NumPy, and we will do this by typing import NumPy as np. And so the first thing that we're going to want to do is to create a copy of the original image to do all our work on. And we will create another variable called lane underscore image, and we're going to set it equal to np.copy and the image we want to copy, which is our original image. And next, to convert our image to grayscale, we simply type gray, which is going to be equal to cv2.cvtcolor. And for the first argument is going to be our source, which is going to be our lane image, and then the code for our color, which is going to be cv2.color RGB to gray. Perfect. Now, let's take a look at the result by displaying our grayscale image instead of the color image. We're just going to change this argument here, and we're going to type gray. Perfect. Then we save our program and run it again for testing. And as we can see, we have our image in a grayscale. The next step is to reduce noise and smoothen our image by applying a Gaussian blur to our grayscale image. And we do this by setting a variable called blur equal to cv2.Gaussian blur. And then for source, we choose our grayscale image. And what we're doing is that we're applying a Gaussian blur to our grayscale image with a 5 by 5 kernel. and a deviation of 0. Now we show the blurred image and run this code. So we change this argument here to blur. We save and we test one more time. And as you can see, we have our grayscale image with a Gaussian blur applied. Now it's time to apply the canny method to detect edges in our image. And we can call this function by typing canny and setting it equal to cv2.canny, which is our built-in canny algorithm in OpenCV. And we apply the canny method to our blurred image. So we type blur with a low threshold of 50 and a high threshold of 150. This means that if the gradient is larger than the higher threshold, then it is accepted as an edge pixel, but rejected if it is smaller than the lower threshold. And if the gradient is in between the thresholds, then it will be accepted only if it's connected to a strong edge. And to see the result, we display our canny image and we run our code one more time. So right here, we change this to canny. We save our program and we run again for testing. And as you can see, we now have a picture with a black background and white highlighted pixels according to our threshold. Next, we will clean up our code by defining a new function called canny, which takes in an image and then returns that exact same image with the canny method applied. As you can see, we get the same result, which means that everything is okay. Now, we will be focusing on this triangular region right here, which in fact houses the two lines that we're actually interested in. This one right here on the left, and this one right here on the right. This means that we will have to create a mask. And we will do this by defining another function called region of interest, which also takes in an image and returns a mask. So we set a variable called polygon equal to a numpy array with our triangle's vertices. So we do np.array, and beforehand I calculated the triangle's vertices and it came out to be the following. The first one being 300 pixels in the x-axis and 700 pixels in the y-axis. The second one being 1100 pixels in the x-axis and again 700 pixels in the y-axis. And then the final and last one is 550 pixels in the x-axis and 250 pixels in the y-axis. Perfect. And then we set another variable called, oh, my bad. Another variable called mask equal to np.zeros_like, and we choose our image. And what this will do, basically, it will create a black image the size of our canny image. So it's just like our background. And the next thing that we will have to do is to fill our mask with our polygon using OpenCV's fillPoly function. So we type cv2.fillPoly And for our first argument, we will choose our mask. And for our second argument, we choose our polygon. And the third and final argument is the color we want our polygon to be. And in this case, it's going to be white. So we set it to 255. And lastly, we return our mask. And then we will now test this by showing the return value of our function, which we will do by changing this right here to region of interest, and we're going to give it our canny image. Oh, canny image. We're going to save and run the program for testing. And as you can see, we have a black background and our polygon in white, which is what we wanted. Now, the next thing that we're going to want to do is to combine our mask with our canny image to only show the lines in our region of interest. And we will do this by typing masked underscore image and setting it equal to cv2.bitwiseand. And the images that we're going to choose is our image and our mask. And what this does is to compute a bitwise AND between the intensity values of the two images. And given that our image of the triangle has a black background with pixel intensity values of 0, 0, 0, 0, computing the AND operation on our canny image will always result in 0, 0, 0, 0, turning all the white pixels in our canny image to black. And the white triangle having pixel intensity values of 1, 1, 1, 1 will have no effect on the region in our canny image, resulting in an image with edges detected only in our region of interest. To test this, we will return our masked image and create a new variable called cropped image to save the return value and display it. So right here, we will change this to masked underscore image. And as we said, we're going to create a new variable called cropped underscore image and save the return value of our function, region of interest, passing in our canny image. Now we save and we run the program. And as you can see, we're detecting lines only in a region of interest in this triangle area right here. Finally, what we're going to do is to detect lines in our cropped image and display them in our original image. And we do this by creating a new variable called lines and setting it equal to cv2.halflinesp, and our first argument being the image where we want to detect our lines, which is our cropped image. And as we can see, the second argument is a distance resolution in pixels, and for this we're going to choose 2. Then our angle resolution in radians, and for this we're going to do np.pi over 180, which is simply 1 radian. And for our threshold, we're going to choose a threshold of 100. And then this next argument is just a placeholder empty array. So we're going to do np.array and declare it as empty. Then our next argument is a minimum line length of 40. And lastly, a maximum line gap of 5, which is the maximum allowed gap between points on the same line to link them. And to display these lines into a real image, we will define a function by typing def display underscore lines, which is going to take an image and the lines we detected. Next, we will create a black background the size of our original image by typing line underscore image equal to np.zeros_like our image. Then, if lines were detected, we will iterate through them and save their values by typing if lines is not none, and for line in lines, we will save their values into 4 different variables, which are x1, y1, x2, y2. And to draw it into our black image, we will use the OpenCV function called cv2.line. So we will type cv2.line, which draws a line segment connecting 2 points. And we will draw our lines in our line image. So our first argument will be our line image. And then the second argument is the first point of the line segment, which in this case will be x1, y1. And then our third argument is the second point of the line segment, which will be x2, y2. And for our fourth argument is going to be the color of the lines, and we're just going to choose a nice cyan blue, which has a code of 255, 255, and 0. And then our final argument is just the thickness of the lines, and for that we're going to choose a thickness of 10. Perfect. Now we just return our line image, and we save it into a new variable called line underscore image equals display lines, and we pass in our lane image and the lines that we detected. And to display it, we just change this to display our line image. We save and we run our program one more time. And as you can see, the lines right here in cyan blue are the lines we wanted to detect in our region of interest, which was this triangle from earlier. And this is really good. Now, the last thing we want to do is to blend this image into our original color image by creating a variable called final image and setting it equal to cv2.addWeighted. Which will take the sum of our color image and our line image. And so for the first argument, we choose our lane image with a weight of 0.8 and our line image with a weight of 1. So our line image with a weight of 1 and a gamma scalar of 1. So to display this, we've simply changed this into our final image. We save our program and run one last time. And as we can see, the lines are displayed on top of our lanes. And with this, we just learned how to identify lane lines in a picture of the road. So in today's video, we went over the role that edge detection plays in self-driving cars and a small program that processes a picture of the road and detects lane lines. Thank you so much for watching, guys, and if you guys have any questions, feel free to email me at jtiznalo@sdsu.edu. See you in the next one.